So both methods which has an initial result. What's the initial result? That's meaning when, even though you do the gradient descent, any approach, okay. If I do like I do this way. Okay. This should be smooth. So if I curve like this way, so if your initial result is suppose, if your initial result here, it's not easy to reach the global minima. If your initial result is here, this ball will fall along this direction. So we have a local minima and the global minima. And you can reach the final result here. So initial result for any kind of evaluation process is very important. So if your initial result somewhere like here, far away from this global minima, and probably your solution is incorrect. So that's why we need to have an initial result. But initial position, basically we can solve it by corresponding solution or pseudo inverse. In order we can have initial position here. And back to here. So the situation use LM is that we have a ground truth. The situation if we don't have a ground truth, we use the EM, expected maximization. So we mentioned about this one before. E is the average value, average approach. And M is the maximal likelihood. It's the Gaussian model we explained that one. Okay. So for the reinforcement learning, right now people still try to develop in reinforcement learning. Reinforcement learning is kind of self-learning. Sometimes they don't have a labeling. So it's the unsupervised learning. So for unsupervised learning, sometimes you can use EM method to solve the solution. Okay. And the last one is the Lagrange. And I said right now many loss function before loss function only here, but they don't solve it using LM because LM is the second derivative is a nonlinear approach. Is complicated. So right now most of the learning method use gradient descent to solve these problems. Okay, but they have a mean Bayes normalization, so they have mean value here. So mean square difference use gradient descent. But gradient descent is a kind of linear approach. Okay, but the better method is LM. So that's why but it's complicated. So far, people use deep learning, they don't use LM, or even they don't use EM to solve it. But last time I told you, last time I told you that people already published paper. This famous guy, Hinton, right? Hinton is very famous, Google brain at Toronto University. They already published paper try to solve it use EM method. Okay, to solve the loss function. And they prove there's a better result, but it's still complicated. So we don't need to use it until it's getting like mature. So back to here. So It's easy because when we solve using the Lagrange approach, we still can use the gradient descent method to solve Lagrange approach. So people don't use EM, don't use LM. So right now, recent 1 year, okay, the paper is getting more paper using the Lagrange approach to solve it. And Lagrange approach, when do the machine learning, people use supportive vector machine, SVM. They use Lagrange. SVM, why is better? Because they use Lagrange approach. They have a constraint. This original one, this one equal to this one. This part equal to this part. But this part has no constraint， 就没有限制它。那没有限制它变成是这里，这里范围没有限制，就会乱跑。So if you have a small one constraint term, okay, and then it will be stable. We call stable. Also, we call this term we call smooth term， 平滑的 term smooth。有时候称这像 SMOOTH smooth term。因为because if you don't have this term, you'll find this like vibration 就是震荡，有时候会震荡，很剧烈。那有这个 term 加进来以后会比较 smooth， 收敛会比较平滑这样子。所以他们用这个 term 来，就现在越来越多 paper， 那这个 term 也是一个 outlier term， 外在的杂讯都去除掉这样子。OK， 你后面会看到越来越多这种 paper， 我相信你才刚开始这个。那记得 all of those methods are not new. Because right now, step by step, they feel, okay, this deep learning is mature, so let's start to move some method from machine learning to deep learning. 它一步步把 machine learning 的一些好的技巧搬过来 deep learning 这边用，还在搬，还有很长一段路要走。So that's why this class, I'm not focused only on the deep learning, because I need to teach you the basic computer vision and basic machine learning method. In order you can understand what's the deep learning going on. 我是要教个基本的，因为教这些基本，你以后才，因为你毕业以后你要自己学嘛，没有人教你。那实际上很多还是要慢慢从 machine learning 搬过来。那有时候你要去了解 deep learning， 假设了要了解更深，你可能要回去稍微了解一下 machine learning 的东西，这样子。OK。So back to the calibration. So our purpose here is try to remember we try to reconstruct based on the 2D image and reconstruct to 3D world. Based on the 2D image information, directly reconstruct to 3D world. But in order to complete this work, we need to know the distortion parameters. We need to know, especially most important one is the projection matrix, also for intrinsic parameters. 5 intrinsic parameters, also called projection parameters. So this from 3D project to 2D, or from 2D reproject to 3D. But from 2D to reproject to 3D, we need one more information that's called depth. So our new camera all have a depth image, depth information. That's 3D. So 3D is RGB plus D. Okay, and this accuracy parameters. So the equation is here. So we know the chessboard here. Okay, we know the image here, the corner here, and we try to solve the unknown parameters here. Okay. So this is a chessboard, right? So we know the position, each one. It's 2 centimeter, 2 centimeter, but it can be any kind of size. But you should know this one because we design this one. Okay. So here. So we try to solve this one. Actually, the purpose is try to solve this equation. So this is a corner. We know the corner of chessboard. 这些点是用那个 use the corner detection to detect the corner position of chessboard. And this estimation result. Okay, estimation. So they have parameters A as intrinsic parameters. K1, K2 is distortion parameters. The RT is rotation translation, and M is 3D position of chessboard. 3D position of chessboard. So we given this one, given M, given small m, and we try to solve A, K, RT. So that's time. This equation is here. So become this one. Because we use chessboard, so chessboard they don't have a z. I mean z equal to 0， 因为它很薄嘛，我们就把它当成一个平面，所以把 z 当成0，所以 R3 is deleted. So we have this equation. So this is 2D, the 3D position, but it's a chessboard, so only have x, y, z equal to 0, and we try to solve this one. And we solve this one using this equation. Sum of square, summation of square and difference. 相减嘛 summation, square, difference. But I told you this equation is from this equation. Okay. But this equation is equal to the exponential term of Gaussian probability. This term is equal to the exponential term of Gaussian distribution, exponential term. Okay. But in this case, let's assume that the standard deviation all are the same in 3 directions. 就每个轴的那个 x、y、z 轴的那个单位数一样，就把它达成就 identity. So become this one. Okay. So this is the result, the detection result image. And this one is estimation. So this term, we try to solve this term. So this term, this one equal to this one. And this norm is UV. And this term is estimation is from 3D. This one is a previous one, right? It's this one. H is you want to solve H. So this is a homogeneous term and become equation. Okay. So this homogeneous term, but we try to solve U and V, so become this term. So this part equal to this part. So based on this one, we try to solve the unknown H. H is H equal to this one, A, intrinsic and extrinsic parameters. 这个 H 是包括内外部参数这样在一起的，所以我们要先解 H， 就是这个 homogeneous matrix 的这个 homogeneous 的 H 这样子，就是这个 term。那就是这个就是我们要解的。This is what we try to solve. Okay, so we try to solve this one. This homogeneous term and become this one. So the unknown is H. So we start to transfer again. The transfer 就是那个 reformulate 就重新组织变成这个。So become Lx equal to B equal to 0. So become this term. And this known and this unknown. Because you cannot use this one. So this one is this unknown, this known, and they combine together. You cannot solve it. You should separate. So separate them to be this is a unknown term, it's known. M is 3D position. UV is a 2D corner position, so become this one. For detail, for detail I write here. This details. 我帮你把这个写在这里 ，detail 在这里，这样就这个 term。So this become ax equal to b problem, b equal to 0. But here, remember, ax equal to b. Sometimes we try to solve a. Sometimes we try to solve x. In this case, I said ax equal to b. Here's lx equal to b equal to 0. So sometimes we try to solve L is the matrix, or sometimes we try to solve x. But in this case, we try to solve H. And H has a 3 by 3, 9 elements. Okay. So when we solve this Lx equal to 0, and this problem, we will use, this problems back to here. Back to this table. We use closed form solution. If ax equal to b, b doesn't equal to 0, we use a pseudo inverse. So that case is ax equal to 0 problem. So we use closed form solution. Closed form solution is this A. We use a singular value decomposition. 因式分解 become u w. If this is a covariance symmetric 对称的话，就 u w u. If not symmetric, it become u w v. And u is an eigenvector. W is an eigenvalue. Okay. So back to here. So we try to solve this one. The way we try to solve is based on this one. This is known. This is 知道的 3D point, 2D points. So based on this matrix, it's here. Okay. We use a singular value decomposition, 因式分解 so it become this one, UWVT. Because this term cannot be 0. 这个 term 不能零啊。这个乘这个 equal to 0. Right? 这个 term 是我们要求的。We try to solve this one. So that's meaning there exists 0 here. So this term become UW. U is the eigenvector. So when this term become original Lx equal to 0, right now become divide times L. So LLx still equal to 0, the same. 你要乘一个 L transpose term 还是等于0。那这个 LL 等于0，那就是变成 LL equal to UWVT times x equal to 0. Because this x, this one cannot be 0. 你这个 term 是你要求的不能0，所以一定是这个 term 有0存在。This term exists 0. So that's meaning what? Meaning U is eigenvector. Eigenvector is not 0. It's vector. So there should be W should be 0. So that's meaning based on we try to find the minimum, the small eigenvalue. Small is close to the 0 or equal to 0. 就找到 W 那个0的那个 eigenvalue. 它的 corresponding eigenvector. That's your solution. Remember, this is a multiple equation. 这是一个联立方程式啊。This is a equations, multiple equations. 这联立方程式的其中一组解会让这个答案等于0，那就是 eigenvalue 就对应0的那一组解的 eigenvector. So your solution eigenvector will be the solution for this one. So that's your answer. 可以啊，这是解。This is kind of one kind of optimization solution. 这是最佳化的解法之一，用 eigen 的方式来解。So the eigenvector, eigenvalue, the singular value decomposition is one method to solve Ls equal to Z problems. Okay. So you know this one. So you have this result. So after you know this result, and this result equal to intrinsic parameters times extrinsic parameters. H equal to this one, and this is scaling term because it's homogeneous matrix of scaling term. It doesn't matter. Okay. So based on this one, what kind of information we can continue to use? Because we have a rotation term. So in rotation of coordinate, 那个轴的 rotation， 它有什么特色 ？rotation 有什么特色？第一个轴跟轴之间 rotation the axis the R1 will be of the normal to R2， 轴跟轴之间要垂直。And the first constraint is that R1 of the normal is this way to the R2, so it's 90 degrees here. The second is that each axis should be unit vector. 每个轴的每个轴都要单位向量，就这个本身你把它当平方，平方这等于1这样子。So there's two constraints. So that's meaning for any axis, it should be of the normal vector. In coordinate, any axis 每个轴 it should be of the normal. What's of the normal mean? Of the normal meaning orthogonal plus normalization. Of the normal 的物理的性质就是它一定要互相垂直，而且它是单位向量 normalize 嘛，单位向量 of the normal. So we use these two kind of constraint. We can try to solve this implicit and extrinsic parameters. So based on this equation, so it's of the normal means that the inner product equal to 0. So this inner product, this one here. Right? So the R1 equal to this one. So A equal inverse to here. And R2 equal to this one. So R1 inner product to R2 equal to 0. So this will be the equation. And this unit vector. So that's meaning if this square here, this inner product will be the same and equal to what? This one. So this one equal to this part. Both one equal to this part. We reorganize become this part. So finally, we have two equations. One is this one. The second is this one. So we reorganize. You don't need to check it, just skip this one. Skip this one. So the result becomes this one. This one. What is this one? There's B. I will try to say it here. Sorry. Try to say it HBH, this term. What is this term? This term equal to both this term. And then define A inverse this one to become B. 那把这个定义成 B， 这两个先定义成 B。这是一个 one equation, the second equation. So after we reorganize again, so become this one. Previously, the B is here. B define B equal to A inverse times A inverse. So this one reorganize become this one, and this one is actually this one. So what will we try to solve? Because we know V is equal to H. So we know H here. We doesn't know B is this one. So again, it's a S equal to 0 problems. So we use the same, use closed form solution to solve B. And then so B can be solved. Okay. And the exam, I don't do this one, just that you know. And all the source code are written by like OpenCV. OpenCV already provide you this kind of source code, and the calculation result is good. So finally we solve B from H, and then we can solve all the intrinsic parameters. After we solve B, we can have intrinsic parameters. This is B 嘛，是 B 出就记出来了。But how about extrinsic parameters? We'll continue to solve it. So for the R1 axis, R1 这个轴 become this result. R2 become this result. That's okay. But where's R3? R3, because this kind X, Y, and Z will be cross product of Rx time and cross product R2. Right? Cross product Y 那个 Y 极嘛 cross product. 因为三个轴互相垂直。The three axes should be orthonormal to each other. So R3, because it's from R1 cross product to R2, so R3 will orthonormal to R1 and R2. But right now has problems. The problem is R1 and R2 are not orthogonal. R1 and R2 so far are not orthogonal. 只要这里的时候 R1 跟 R2 是没有垂直，没有垂直，你 when you do 3D reconstruction, you will find one problem. Sometimes, suppose you face, after you get a result, sometimes the face is too thin, sometimes too wider. 会变形 That's because your R1 and R2 or Rx and Ry are not orthogonal. Any 3D reconstruction, the result here is problem. Okay, so we continue to solve R1 and R2 using what kind of method? This is page 41. Page 41. We need to make sure Rx is orthogonal to R2. Again, we use the singular value decomposition method. So based on the R, right? Sorry, this R. So the way we do is just don't care about anything, just check here. So the solution, this is from a paper, but for you the easy way, sorry, is here. Sorry, easy here. So for the R1, R2, you do singular value decomposition, become U, Z, V. And then you change the Z, become identity. So your solution will be R equal, the recovery become U times V, because U is the eigenvector, is orthonormal. V is also the orthonormal. So this is rotation matrix is orthonormal. So both orthonormal matrix times together, your R1, R2 will be orthonormal. 说这个解法上，这个不是很容易解释，但是我大概简单讲，就是说，你把这个 两个 R1、R2 经过 SVD 做了以后，它就变成把 Z 用 I 取代，就 identity 每个方向都是一样的单位，就变强迫 Z 就变成 identity， 然后直接 U 乘 V， 因为 U 是个 orthonormal 的 matrix，V 也是 orthonormal matrix。orthonormal 那两个 orthonormal matrix 相乘，所以 R 就两个就垂直。这样你解出来这个就 so this is solution, reconstruct solution. So if you don't do that one, this one won't be 90 degrees. So after you do that kind of process, this will be 90 degrees. 这很重要，不然会变形。Okay, so we solve the intrinsic and the extrinsic parameters. And the last one, what we try to solve is distortion matrix. Okay. So back to the page 6 video here. So we solve the RT, we solve the K. The final one is the distortion. With distortion problem. So there are two kinds of distortion. This is for OpenCV in this chapter. It's good, very good. So they explain very good calibration, because for any 3D reconstruction, this kind of process is very important. So they have two kinds of distortion here. The first one they call radial distortion. Radial distortion is this one. So far, any camera has radial distortion. Any camera has radial distortion. And the better, the expensive camera has small distortion. Cheaper one will be distortion will be big. Okay. So we try to solve this one. So this is because the lens. So we try to solve K1, K2, and K3. Try to solve this one. This is because of the lens, because your lens is circle. 你那个镜片是 circle 所以它会有这种 lens distortion 这样子。But the second one, this one is groove, is because when this is your sensor, camera is a sensor, right? And the sensor need to attach to the camera, the button. But sometimes if you attach it like this one, 斜掉了. You attach, you glue the machine, try to attach it here. But this one is not parallel. So there was a little bit distortion. So your image will become this one. Originally it should be square. Square or rectangle. But because this is some problems when you glue this one, company do that. So there's kind of distortion. Okay. So if you have a better product from the Germany or Sony, they have some high price camera. That's meaning they have high quality of this one. Because most people doesn't know how to do the calibration. And for the tangential distortion, there's a P1 and P2. And I copy this one from the OpenCV book, because so far I see in that chapter of OpenCV is the best book talk about the distortion. So we just try to solve P1 and P2. So total, there are 5 distortion parameters. 2 are for the tangential distortion, and 2 K1, K2, K3 are for radial distortion. And in this in this paper, they only do the example about only 2 terms, but actually the same, all is the same. And the other problem is here. What kind of problems? I still confused. Some paper or some book, they say here, K1 X, Y. They say this is a distortion free, meaning distortion result here, and distortion result here. Some paper reverse. Okay, and I'm afraid. Originally I know, but after doing more papers, or student ask me and then confused. 常常有时候本来都很清楚，然后有时候学生弄错了，搞错了，然后弄久了以后我自己搞混了。那我这意思是说，有这2个道理，哪一个是 distortion， 哪一个是没有 distortion， 我现在搞混了。那书上也有书或 paper 也是都乱写，都是一下写这样，我也搞混了这样子。但是你大概知道就好了，因为那个程式都帮你写好了，所以这个不用太不是说不用 care， 就是你大概知道，就有一个是假设这是有只要这是有 distortion 出来，就是帮你程式让你弄出来就没有 distortion 这样子，所以大概让你知道一下。好，那这个把它弄小一点。 我们来看这是 one example， 这是 one example. This one. What I say is that here is that ax equal to b, b doesn't equal to 0. This is what one solution. Only k1 and k2. Actually here is should be this k1, k2. So this k1, k2. There you will see that sometimes confused, but you don't need to care too much. I just give you the information from the book, OpenCV book. But the easy way we check this one. So actually they have 5 parameters here. Okay? But assume we have only 2. So we reorganize this one. So become this one. So this unknown k1, k2 unknown. This means the distortion parameters you want to solve is this one. But actually you have 5 here. And suppose if in our case, suppose this is distortion free. So distortion free is meaning the one you try to solve the answer. And distortion, distortion is what? Distortion is right now you have a solution here. Because we already calibrate, we already solve RT, we also solve K. So any 3D, the chessboard point, they will project to here. Actually, this is undistorted. 刚刚算的那些倒置到这里来的。The one we just said, tell you the answer is from here. You know this one. And after RT, after intrinsic parameters, so your solution, you know this one right now, based on previous work. And this is what you image can, you take the image. So this is what image you have. The corner detection is here. Use corner detection to detect the image. So image is here. And this one is already you solve from here, solve to here. So right now, based on, we call this undistorted, this distorted, and we try to solve the distortion parameters here. 这样知道吗？这个你已经解到这里了，这是实际上2的，还可以解中间这一个，这样，就是，那我们要解的话，就是用。就在这里。那我们解 we solve k1, k2. So in this case, is ax equal to b, b doesn't equal to 0. So we solve this one. We solve k. So become this one. So how can we solve this one? Because this d, we don't know whether they can inverse or not. Not any matrix can inverse. So we assume this cannot inverse. What I mean is, no matter it can inverse or not, or cannot be inverse, we all can use this method to solve it. So how can we solve it? Is that we originally have d, and we times d transpose with each side. So we have one more term here, one more term here, and then this can has an inverse. So we inverse this one, so become this one. So this is called pseudo inverse. When people say closed form solution, what's closed form solution? It's ax equal to 0. That's called closed form solution. When ax equal to b, b doesn't equal to 0, and we solve it use a pseudo inverse. So this is called pseudo inverse. So this is called pseudo inverse. So this is the solution. Okay. So you know the both methods. So we solve it. This is the same case. Okay. So far we have an initial result of A, K, RT. So we have an initial result, this one. And then we try to solve using LM method. And this method LM, you just put into the equation and they'll solve it. Because LM is the other, I think when you take the course of optimization, 叫郑老师吧，我忘记了，的体健修所的老师啊，我鼓励你们去修那门课，就最佳化的最佳化市场你要去修了。我这边讲的最佳化是比较实用的，比较因为我只懂我只懂这些，那活到这里每次都可以解决问题这样子。OK， 那 LM method in the internet they have some LM method the source code for you. OpenCV also has source code for you. So after you have initial result and you call this method and it can solve and have a better result this one. And LM method they can make sure compare with gradient descent. This method has a more better result to find the global minima. LM method or EM method compared with gradient descent method, they have a better result to find the global minimum. Why we don't use that one in the deep learning? Because it's complicated. It's not easy to solve 10 million parameters. Okay, in machine learning, we don't have such big parameters. 我们 machine learning 没有那么多不知道的参数，都很少，那边太多了。但是那些数学很强的那些 superman， 他们就在解这个问题。我劝你不要解这个问题，拿来用就好了，不适合解这个问题。但是你如果是应用数学系的，纯数学系的，你可以冒险没关系，你愿意冒这个险。但是你如果真的要读学位的话，是不要冒这个险。那你们老师如果要冒这个险，值得鼓励他，但是个人劝你不要冒这个险，因为这个不容易，真的不容易。OK， 因为那个是图腾讲的，那几个是图腾讲的，就是 computer 的最高图腾讲的人在解。好，那So I solve all the solutions. OK， 那就这边好像都讲完了，对，我都讲完了。后面after this one you don't need to check it, just put more info, put some exclamation result. So the final, you don't need to study all of those, just study the lecture I teach in the class. 那上次有刚让你看到这个嘛？上次有看到这个是这个。先到的样子。好，那我们先下课。So next lecture we'll talk about 3D sensors. Okay. We take a break. Thank you.